So we talked about distances from a point in a plane, but we want to talk about other ways that we can use what we know about dot and cross products to find distances for other objects in space. The first thing I want to note is that if I have two planes, the way I can figure out if they're parallel is that they would be normal to the same vector. Think about it, it makes sense. If I have two planes that are right across each other, the normal that shoots through one will shoot and be orthogonal right through the other, as demonstrated here. So if I want to figure out the distance between two parallel planes, because the distance between two non-parallel planes, they should intersect, right? But if you have two parallel planes, to find the distance between them, what we do is we find a point Q in this plane and a point P in that plane, and we perform the distance from this point to this plane the way that we found distances in the previous section. So that one's fairly straightforward. The only big difference is we have to find a point in this plane, and then we can do the same process. Now, if I want to find the distance between point Q and a line, well, that one we haven't done before. We haven't found the distance between a point and a line. And it's pretty close. It's pretty similar to the same idea. But if we look at this, what we have is if I have some line that's described by a point plus t times some sort of direction vector. So if I have this kind of setup and have a point Q, well, if I draw a directed line segment from P to Q, it creates an angle with that direction vector V, and it creates this right triangle, right? That distance here is really, it's the magnitude of PQ times sine of the angle between them. And we want to figure out the best way to get PQ times sine of the angle between them. Well, if you think about the way that a cross product works, if you remember, the magnitude of a cross product, U cross V, is the magnitude of U times the magnitude of V times sine of theta, right? So in this case, you could think of it as the magnitude of PQ times the magnitude of V times sine of the angle between them. But we don't want that magnitude of V, so we just divide by it. So if we take the cross product, take its magnitude, and then divide out the magnitude of that direction vector, then we can guarantee that we get the result we want. And that's how we get that distance. And finally, we have distance between parallel lines L1 and L2. So you may say to yourself, well, of course I can figure that out, or I don't have to worry about non-parallel lines. There's kind of an interesting case in 3 dimensions. In 2 dimensions, if you have two lines, they're either parallel or they cross at some point. But in 3 dimensions, you can have what are known as skew lines. So imagine the case where I have my arm pointing straight out here, and it goes infinitely in this direction and that direction. I have this arm that points directly up, and it goes infinitely in that direction, infinitely down. Now, if it goes down this side here and across the side here, they actually never interact. So they're not actually parallel, and they never cross over. So there's a little more advanced mathematics that you're going to want to employ if you want to find the distance between non-parallel and non-intersecting lines. But for the case that we have parallel lines, and the way that you know that lines are parallel is that they'll have that same direction vector, right? So if they're going in the same direction, they must be parallel. Similar to how in 2-dimensional space, lines were considered parallel if they had the same slope. Same idea here. So if we have two lines, then all we really need to do is, it's kind of the same way we did it here. When we had two planes that were parallel, we found a point on one of the planes and then just repeated the process we've already done. So the same idea is here. If I have two lines, I find a point on the second line, and then I use the first line the same way that I did in this example with this kind of setup. So if I drew a straight parallel line through here, it would be the same idea. And so we're going to do some examples that show how we actually compute these when we have real numbers.